So my talk is about categorification of Donaldson-Thomas invariants and its relation to the Dolbeault-Langlands conjecture. That is, so this is from Donaldson-Thomas invariant. So this is originally some integer valued invariants counting stable sheaves on Calabian seafolds.
And you can also, maybe you have to press more in order to
press more.
Yeah.
But it's okay? Or
it's okay.
So then this is counting some objects on Calabian seafold, and we are going to discuss about its categorifications. So this is categorical DT theory. So this is the DG category, which should recover the original invariants. So these are the invariants counting objects on Calabian seafold, like points or curves, and this is some categories. And this is more abstract object, although this is more explicit object. But by categorifying these enumerative invariants, we can see many interesting phenomena. And I'd like to discuss one of the interesting phenomena that it has some application to the Dolbeault-Langlands conjecture. More precisely, I would like to give some precise formulation of its conjecture. So this is some sort of duality between the Higgs bundles. So then, but today, I'm going to talk about some introduction about DT theory. And also give some motivation toward this categorification. I'd like to explain why I want to categorify. And then in the last 3 lectures, I will focus on this Dolbeault-Langlands. So then first I give some introduction about DT theory. And this is defined through the moduli theory of coherent sheaves on varieties. So let me recall about moduli spaces or moduli stacks of coherent sheaves. So let's take X. X is smooth projective variety. So in this talk, everything is over complex number field. And also take V in the element of the singular cohomology group. So then let's consider some moduli space of coherent sheaves with this numerical class that is MV. So this is moduli space. Or more precisely, so I'm considering moduli stack of coherent sheaves whose Chan character equals to V. So abstractly, we take this as some algebraic stack, maybe locally of finite type. But even if you fix some topological class of E, it is usually not good moduli space which you should want to consider. In particular, so this is not quasi-compact. For example, let's consider the case that X is just P1 and V is element of like 2 and 0 in H0 plus H2. So this condition means that the rank is 2 and the degree is 0. And in that case, the set theoretically this moduli space consists of some direct sum of line bundles. So let's only consider the just local free sheaves. So this means that this is a substack consisting of only locally free shifts. So then it is known that every vector bundle on P1 decomposes into the direct sum of line bundles. And every such ranked vector bundle consists of only OP1 A plus OP1 minus A, where A is bigger than or equal to 0. So let's write this vector bundle as FA. So from this, we see that this is not of a finite type stack, because if we consider the global section of this vector bundle, it goes to infinite if you take A to be infinite. And in fact, if you consider F0, this is the most generic one, that is the substack of MV consisting of this point forms open substack of this one. And if you take some degeneration of this direct sum OP1 plus OP1, then it degenerates to the OP1 A plus OP1 minus A. So we have this. And similarly, you have this chain of inclusions of open substacks. And it does not converge, so that this is not quasi-compact. So usually, when in algebraic geometry, when we consider moduli space, we don't consider such a big moduli space, and we consider only some semi-stable shifts. So I'm going to now define the semi-stable shift, but in this lecture, this is the only one which we want to consider in algebraic geometry. But later, maybe in the last lecture, I will also come back to this non-quasi-compact moduli stack. But today, so in classical in defining DT theory, we have to first fix some stability condition to construct some nicer moduli space. So there are several ways to define stability condition, but the classical one is using ample divisors. So let's take fix H. So this is the ample divisor on X. And let's take for each coefficient shift. So let's take its Hilbert polynomial. So this Euler characteristic is a polynomial in M by the Malon theorem. And the degree of this polynomial equals to the dimension of the support of this shift E, F shift F. So A0 is non-zero, and D equals dimension of the support F. So then we take the quotient of this polynomial by the coefficient of the leading term. So this is called the reduced Hilbert polynomial. So for example, in the case of that X is one-dimensional, so this is the equivalent to giving the slope of this coefficient shift. That is the ratio of the degree and the rank of the shift. And for example, when the dimension of the support F is the dimension of X, so then this is like D plus. So this is like the ratio of the degree and the rank of the coefficient shift. But we also have some information of the some higher chunk characters. So then, classically, we say that a coefficient shift on X, we say that this is semi-stable, H semi-stable or H stable, if the first condition is that that E is a pure shift. So So this means that there is no subsheaf such that dimension of support F is less than dimension of support E. For example, when the dimension of the support E is the same as the dimension of X, this condition is equivalent to that E is torsion-free sheaf. And the next condition is that we have the inequality of this reduced Hilbert polynomial. So this is called reduced Hilbert polynomial. For any subsheaf. For example, in the case of dimension 1, this is the same as the inequality of the slope of E and F. That is the ratio of the degree and the rank of E. So then we usually consider only the semi-stable sheaves or stable sheaves to construct modular space. That is, so first we consider this non-quasi-compact modular stack. But we have open substack consisting of semi-stable sheaves and also consisting of stable sheaves. So these are the open substacks. And the good thing about considering semi-stable sheaf is that, so these are now finite type stacks. So in particular, they are quasi-compact. Moreover, there is some approximation of these modular stacks to some varieties. For semi-stable sheaves, we have some natural map from here to some projective scheme. So this map is so-called the good modular space. So roughly speaking, so this good modular space is that this is a stack. So this is something like the quotient of a variety by some group actions. And this is like taking the honest quotient space. For example, if you consider a fine space Y with some quotient of some reductive group, say for example like G of N. If you consider this quotient stack, then there is associated quotient space. So this is an example of the good modular space. And it is known that every good modular space for RT stack is heterologically modeled in this way. So you can just think that this good modular space is something like this. And also we have also such good modular space for stable part. And we have this Cartesian square. So this is now open. So this is projective scheme, but this is open substack. So in general, this is not projective. So sometimes it is not proper. But the good thing about this left map is that so this is now so-called the GM job. So this is roughly saying that every automorphism group for this stable sheaf is just the GM. So this is a well-known fact about stability that if you consider stable sheaf, then there is only scalar multiplication for the automorphisms. This is not true for the semi-stable sheaf. For example, if you take the direct sum of stable sheaves with the same reduced Hilbert polynomial, then it is like GL something. It's not necessarily GM. But for stable shifts, this is GM. Anyway, so we have the nice projective scheme and its open subspace. And the behavior of the modular theory really changes if this is equal or not. We say that the modular theory satisfies the we say that it satisfies semi-stable equal stable condition by definition. We say that this holds when this is equal. It depends on choice of the numerical class V, of course, on given variety X, choice of V, and also choice of ample divisor AH. But if this condition is satisfied, then this modular theory is very nice because in this case we have the equality of the honest modular spaces, and the modular space of stable shifts is in fact a projective scheme. And there is not much difference between the stack and the scheme. For example, in the case of C equal P1, in the previous example, in that case, this is not satisfied unless the rank is 1. For example, this MSS to 0, it consists of only the direct sum of OP1. The automorphism group of this one is not GM, but GL2C. So this is B GL2C. And its good modular space is just taking the spec of the invariant ring. So this is nothing but just one point. So this is just a point. And in this case, as I said, so this is not SS but S. So far, so this is a general theory about modular spaces in arbitrary varieties. But now I'm going to restrict to the case of Calabian seafold, and then define the Donaldson-Thomas invariant. So now let's take X to be Calabian seafold. So this means that the complex dimension of X is 3-dimensional, and the canonical line bundle of X is trivial. So in that case, there are some special property of this modular space of stable shifts. So let's take point P equals E in MSV. So this is now a stable shift. So then the tangent space of this modular space, so this is easily deduced from the deformation theory that tangent space is given by the x1 of EAE. So the tangent space is, so this is a space of the infinitesimal deformation of this shift E. This is also saying the same as the map from the spec of C epsilon over epsilon square to this modular space which goes to the origin to this point P. But there are some obstruction space that if you are given infinitesimal deformation, then there is some obstruction class, so that this obstruction class vanishes if and only if this infinitesimal deformation extends. And this is also known that obstruction space. So this is given by x to 2 of EE. So far, so I don't use anything about the condition x is Calabi-Yau, but when x is Calabi-Yau, there are some special property between the special relation between tangent space and obstruction space. That is, x is C by 3. So then the x to 2 EE. So this is now derived to the EE. So this is due to the Seiyuei derivative. Plus C by 3 condition. So this means that the tangent space and obstruction space is dual to each other. In particular, the dimensions are the same. The dimension of the tangent space and the dimension of the obstruction space are the same. So this is a very special property for Calabi-Yau threefold. So this means that, roughly speaking, we view this moduli space as locally parameterized by x to 1, but with some equations whose value lives in this x to 2. But this x to 2 has the same dimension of x to 1. So this means that virtually speaking, this moduli space has a dimension of the tangent space minus dimension of the obstruction space. So that roughly speaking, we can consider virtual dimension of MSV. So just let's define as the dimension of the tangent minus dimension of the obstruction space. But it may not be necessarily constant for each choice V, but in the case of x is Calabi-Yau, this is constantly 0 by these duality conditions. So this means that the honest moduli space we should consider is should be something zero-dimensional scheme. But in many cases, in most cases, this is not zero-dimensional. So it has a dimension bigger than the virtual dimension. But in enumerative geometry, so when the actual dimension is bigger than the virtual dimension, we instead consider the virtual fundamental class on this moduli space, and then define the invariant. So this is also the case in Donaldson-Thomas theory. And from this observation, it was constructed by Richard Thomas. So there is some zero-dimensional virtual fundamental class. So then, because now this is zero-dimensional, we want to take its integration to get some integer valued invariant. But this is only possible when this moduli space is projective or proper. So this is satisfied when S is semi-stable equals stable condition is satisfied. When SS equals S condition is satisfied, maybe under equals S condition, define the dtv. So this is the integration of this zero-dimensional virtual fundamental class, which gives integer. So this is the classical construction of the Donaldson-Thomas invariant. And it is also shown that this is invariant under deformations of complex structures of Calabrian seafood. So usually this condition is very, very important. And usually this condition is satisfied when this class is somewhat primitive in some in the image of the Chan character map, and the choice of the polarization is sufficiently generic. And maybe the most famous example defined in this way is curve counting Donaldson-Thomas invariant. This is a case when v equal 1, 0, minus beta, and minus n in h0 plus, h2 plus, h4 plus, h6. And here I'm identifying h4 with h2 and h6 with h0. So this is now one-dimensional vector space. And so now beta is regarded as second homologous, and n is in fact, we take n to be integer. Anyway, given this class, then this is the case where SS equals S condition is satisfied. This is because the moduli space, or moduli space of semi-stable sheaves and moduli space of stable, moduli space of stable and semi-stable sheaves are the same, and they consist of ideal sheaves satisfying this condition. So more precisely, I have to fix the determinant of these sheaves, but I omit it. So anyway, under this condition, this moduli space consists of only such ideal sheaves. So this is ideal sheaf of such curves, and this is nothing but the Hilbert scheme of closed subschemes in X. So then from this moduli space, we have the associated DT invariant. This is also known as the curve counting DT invariant. So this is because in this case, the stable equal semi-stable condition is satisfied. And this is the one which have very important role in curve counting DT. For example, this is known to be related to the Gromov-Fit invariant. So this is a rational number, but there are quite non-trivial relationship between these invariants. This was first conjectured by MNOP, proven by Pandai-Pixton. In many cases for Calabrian seafood, and also John Pardon for in any case. And for some special case, the structure of the generating sheet is also known. For example, in the case of beta equals 0, in the case of beta equals 0, so the dimension of sheet is just 0. So this is a Hilbert scheme of points on Calabrian seafood. And in that case, this generating sheet is completely computed. Yeah, so maybe I should say that. So here I should also take the determinant trivial or nothing. Yeah, and otherwise, yeah, I can also assume that HMI is 0, so that there is not logically trivial line boundary. So then this is known that the minus q power of the Markov function. So this is for the Markov function that is 1 minus qk minus k. So this is also important in the combinatorics, that each coefficient of this series is so this is the yes. So this is the number of the so-called plane partitions. So partitions of M. So this is a famous formula by McMahon, and so this formula basically appears because if you consider Hilbert scheme of points not on X but for C3. Then you can compute it, for example, by using localizations, and at each Toda's fixed point locus has one-to-one correspondence between such plane partitions. So anyway, so these are the important examples of Donaldson-Thomas invariant. But another important aspect of Donaldson-Thomas invariant is that, so this is first defined as the integration of the virtual fundamental class. But the group-fit invariants are also defined in this way, using the integration of the virtual fundamental class. But in DT theory, you have some special property of the obstruction theory, that obstruction space is dual to the tangent space. For example, if the moduli space turns out to be smooth, then this virtual fundamental class is the Euler class of the obstruction boundary. But the obstruction boundary is dual to the tangent boundary. So in that case, so this is the same as the Euler class of the tangent boundary up to some sign. This is nothing but the usual Euler number of the moduli space. So this is the case when this moduli space is smooth. So from this one observation, you can imagine that this is also written by some sort of Euler characteristic of the moduli space. So this was proven by Kai Behrendt using some constructive function on the moduli space. I'm going to explain about micro-local description. Let's recall that for each point P equal E, in yes, just for simplicity, I write it M. It's V. So locally, so I say that the tangent space of this moduli space is x1, and the obstruction space is x2, which is dual to x1. So this means that at least analytic locally at P, so there is some x1 some analytic open neighborhood and also there are some analytic map. This is so-called Kranich map from U to the x2, so this is dual to the x1. Such that locally, so this moduli space isomorphic to the zero locus of this kappa, zero locus of the Kranich map. So whether this moduli space is in fact zero dimensional or not is how much general of this kappa is. For example, like this kappa is a regular section, so that the zero locus has the correct codimension. Then this becomes zero dimensional. But this is quite a rare case. But anyway, so this is a map from U to the dual to the tangent space of U. Well, this is another way to think about this map is, so this is a section of the cotangent bundle of this analytic space U. So this the choice of kappa, so this kappa is equivalent to that. This is a section of omega U to U. So what was proven by Joyce and Son? So there are several versions of this one, but so the first one was proven by Joyce and Son that so that there is some also maybe by shrinking U if necessary, that there is some harmonic function such that we can take such kappa to be the differential of this function f. So that the Dolbeault differential of this function f gives a section of this cotangent space. Another way to say is that this kappa equals 0 means that this locus is given by the critical locus of this function f. That is, so this moduli space M is locally given by the critical locus of this function f. The critical locus is the vanishing locus of this the Dolbeault differential of f. So this means that this is like the, if you take the coordinate of U, so this is like so this is a very important local information of the moduli space of stable shapes on Calabrian seafloor. So this property is only available in the case of Calabrian seafloor. So then let's define the following function. That is, let's take chi bp to be the minus 1 power of minus 1, Benjamin U, 1 minus topological Euler number of the so-called Milnor fiber of f. So this is called the Milnor fiber. So by definition, this is given by x in U, such that the if you take some suitable norm on U, so then this is less than delta, and fx equals to f0 plus epsilon, when epsilon is sufficiently smaller than delta, and delta is sufficiently small. So this is so one can show that this is independent of the choice of such data, and it, in fact, for each choice of P, we can find such a chart, and then we can associate such a number. So this is some integer valued function on M, and in fact, so this one gives a constructive function on this moduli space. So then what was proven by Kai Behrendt is that the original definition of the DT invariant given by the integration of the virtual fundamental class is same as the integration of this constructive function defined in this way. So this is also again under S equal S condition. We have that dtv. So this is equal to the integration of this constructive function with measure given by the topological Euler characteristic. So this is by definition given by the weighted Euler characteristic. So this gives a constructive function. So each fiber is a constructive set of M. So this Euler characteristic makes sense. And this is a finite sum. So this is again some integer, and they are same. For example, when the moduli space is in fact smooth, so then this function is either some constant function, either +1 or -1. And in that case, so this invariant is the usual topological Euler characteristic of the moduli space up to sign. But in general, this moduli space has some singularities. And in that case, this is not the same as the usual Euler characteristic, but we can interpret this one as some sort of Euler number with the moduli space, which also keeps track of the singularities of the moduli space. So informally speaking, so dtv is something like Euler number with the moduli space. But this Euler number is not only the Euler number, but the which keeps track of singularities of this moduli space. Okay. Okay, so this is the basic story about defining Donaldson-Thomas invariant when SS equals S condition is satisfied. In this case, we have both definitions. We have either integration with the zero-dimensional virtual class or integration with the variant constructive functions. In both of each description has an advantage. So in describing, in the definition by the virtual fundamental class, we can show the deformation invariance of the moduli space. On the other hand, the description by parent function, so this gives very useful in computing the Donaldson-Thomas invariant. For example, we can like cut and paste technique to compute such invariants. So then I'm going to roughly explain about the probably more important case where this condition is not satisfied. So in that case, there are two invariants. The one generalized DT invariant. So this is a rational invariant, and also the integer valued invariant called BPS invariant. So they are deleted by the so-called multiple cover formula. So I'm going to explain about BPS invariant. So roughly speaking, so this is like the DT type invariant without SS equals S condition. So then let's recall the previous setup that let's consider moduli stack of semi-stable sheaves. And it admits good moduli space. It admits open substack of stable sheaves. And it admits also good moduli space. So if this condition is not satisfied, this means that these are strict inclusions. In particular, so this moduli space of stable sheaves is not proper. So in that case, let's try to define the DT invariant in using either one of the definitions in the case of S equals S conditions. But you can see that there are several issues. So first, originally this DT invariant is defined using the integration of the zero-dimensional partial fundamental class. And this semi-stable equals stable condition is used in order to integrate the zero-dimensional partial class. So if we want to consider this the partial fundamental class, then this one does not make sense because now MS is not proper. So we cannot have the proper push forward of the child group. So instead, although the moduli space of stable sheaves is not proper, but we have the compactification by the semi-stable sheaves. We may also try to consider something like this. But this one also does not make sense because we have the nice deformation of structural space on the stable part. But on the semi-stable part, we are taking some quotient by the so-called S equivalence classes that we identify the sheaves with the equivalent Toda header filtrations, so that the nice obstruction theory on the moduli stack does not descend to some nice obstruction theory on this one. So in particular, so there is no nice zero-dimensional partial class on the semi-stable moduli space. Does not have deformation obstruction theory. So on the other hand, we can also try to use this construct definition using variant. We can also try to define using the variant function. So let's let's consider, for example, say integration of the variant function by the stable part. So in fact, this one makes sense. You can define this one. So the variant function exists without this SS equals S condition, and the high-weighted Euler characteristic also makes sense for non-compact scheme. So this one may make sense, but this is not a good invariant. For example, there's an example where this is not deformation invariant. And in order to define nice invariant, we have to really take care of the strictly semi-stable sheaves, which are not stable. So this is not make sense. But not good. And similarly, we can also consider integration over the semi-stable locus. In fact, this one also makes sense. As I said, so the variance function makes sense as Euler characteristic of the mu fiber on the stable locus. But in fact, parent construct such constructive function for any scheme, although it is not given by the Euler characteristic of the mu fiber. So this one still makes sense. But nevertheless, so this one turns out to be not good. And because so on the strict semi-stable locus, we can define it, but there is no reason why we should use it. So still in the same reason, so this one is also not good.
Is it because it's not a deformation invariant or does not give it the right numbers?
I think that for this one, the Joyce proved there is an example where it is not deformation invariant.
In the second one?
In the second one, I'm not completely sure, but anyway, so it is not. There is no good reason why we should consider this one anyway. Maybe I think that there is an example where it is not deformation invariant. But what was done by Joyce and Song? That instead of considering the oldest moduli, so the idea is very close to here. So maybe I think I should say one more case. So instead of this one, we should also consider this one. So now, so the comparing this one to this one, the variant function on this stack is also more reasonable because then this is given by the Euler characteristic of the Müller fibers. But still, this one does not make sense. Because so this involves the Euler characteristic of the outing stack. And usually, we cannot define the Euler characteristic of the outing stack. For example, since Euler characteristic of outing stack doesn't make sense. For example, if we want to consider Euler number of the BGFN, we may want to define of the quotient of the like this, but this is 0. So this one doesn't make sense. Alternatively, if you consider the cohomology of BGFN, so this is infinite dimensional, so you cannot define its Euler number. Instead, what they did is somehow modification of the last proposal. So they did modify this moduli stack so that the Euler number makes sense. So this process involves more notation and some explanation, and this is not the main topic in this lecture, so I don't give its precise construction, but roughly speaking, what they did is consider this kind of sum. So this is the sum of the moduli stack for each fixed reduced Hilbert polynomial, and take its logarithm, and then take the multiplication by GM. So this operation, so this makes sense in the so-called modulic Hall algebra. So then this one is now given like this. So now the point is that so each term, so this is a better stack in the sense that we can define the Euler number. So some sort of stack where the Euler number makes sense. So this is a very deep theorem by Joyce about the so-called absence of pole theorem, that was recently reproved by the so-called intrinsic DT theory project by Tatsuki Kinjo and Hyunjun Chen Jinbu and his collaborators. Anyway, so from this observation, the so-called generalized DT invariant is given by integration of the variant function of this modified stack.
So that one is the so-called Joy-Song stack?
I don't know whether it is called Joyson stack or not, but anyway, so it is, you can say that, yeah, Joyson defined. Yeah.
So parameterized pairs where you have some
No. It's not Joyson pair moduli space. Joyson pair moduli space is a pair given by the E and M. Yes. That's right. So this moduli space is not a stack. This is a moduli space. And you can delete this invariant with the Joyson pair invariant. So then using this correspondence, they can show the deformation invariance of this invariant.
But
so
empty now is defined.
That's right. So the issue about this Joyson pair is that it may depend on choice of section. That is for choice of the twist of the sheaf. It is eventually independent of choice of the M, but you can also alternatively define the invariant using the Joyson stable pair invariant. But here I'm using this log in the motif for algebra, and the difference between Joyson pair invariant and this one is that this is now not integer, but this is rational number. So this is integer value invariant. Yes.
I didn't quite understand the expression you wrote on the left.
Yeah, because I didn't explain. So yes, maybe if you want to know more, I can explain more formally. But so roughly speaking, we can consider some algebra whose element is given by some stack together with map to the moduli stack of sheaves on X, and then we consider the direct sum of this kind of expressions, and there is some algebra structure on this very big space. This is given by some, basically this is given by the exact sequence of coherent sheaves, and so this log makes sense in this big algebra. And so then, if you consider its log, this log means that log 1 plus x equals like x minus this expression. And then if you formally expand log and then rewrite it in this way, then he can show that this one makes sense.
And that is the trivial GM bundle over the moduli.
Yes, this GM bundle is upon because, as I said, so if you consider stable locus, it is a GGM job. So even if SS equals S condition is satisfied, you have to multiply it to have the moduli space which have the Euler characteristic. Otherwise, it is something like the quotient of some space with a trivial GM action. Still, you cannot define the Euler characteristic because the Euler characteristic of GM is 0. But you can just give this contribution by taking the multiplication by GM. So this is called so-called generalized DT invariant.
So nowadays, is it now whether there is a Riemann first stack which realizes this and by some sort of like waiting for one?
I think you mean this the carbon blow up or something? Are you talking about the carbon blow up of the moduli space? Carbon blow up. I think that I know that Junli, Yonfun Kim, and some of us are constructing another construction of this type of invariant using carbon blowing up. But it's not clear whether this is the same as this one or not, I think.
So it's not known whether they are the same.
At least I don't know. So then this is rational number, but we can also define the integer valued invariant. Obviously, so this is a rational number, but it can be defined by the so-called multiple cover formula. For example, we can take So k is some integer. So this means that, for example, we take v in the element of the image of the Chan character map. So this is a finitely generated abelian group. And so this means that v is divisible in this group, in this abelian group gamma. And for example, if v is primitive in here, so this dt and omega are the same. But otherwise, so there are some multiplicities of v. And in that case, we can define omega v inductively by the divisibility of v. So a priori, so this is just a rational number, but it can be shown that this is in fact integer under some genericity condition of h. So this is also due to Davidson-Meinhardt. So under some genericity of h, we can, in fact, omega v is in Z. So this is now called the BPS invariant. And in fact, so this is the same as dTV when S is semi-stable or stable conditions are satisfied. So yes, as I thought, the dTV is the usual Donaldson-Thomas invariant under S equal S condition is like the Euler characteristic of the modular space, but which also keep track of the singularities of the modular space. Informally, we can also say that omega v is also something like the Euler characteristic, but now modular stack of semi-stable shifts, but which also keeps track of the singularities and also some static structures of this modular stack. So the other says if there are some non-trivial stabilizers like GL or something, then we cannot define the Euler characteristic. But so this is Euler characteristic which also keep track of these things. So yes, I just give some examples. So when v equals like multiplication of R7, so this means that the only rank curve shifts, and we consider this shift, then it has the Chan character R000, and this is the isolated point of this modular stack. And let's assume that this is in fact equal. So then one can show that, so this is some direct calculation that omega v is equal to 1 when r equals 1 and 0 otherwise. Another example is that, so when v equals like 0, 0, 0, k or n, so then we can show that, so this is now the counting points, zero-dimensional shifts on X. So this is like minus of the Euler characteristic for n to 1. And we can, so we can imagine that this is something similar to the multiple cover phenomena in Gromov-Hitten theory. So in Gromov-Hitten theory, there is a formula which expresses the genus zero Gromov-Hitten invariant in terms of multiple cover formula, where this omega is replaced by the genus zero buffer invariant, and this 1 over k square is replaced by the 1 over k cube. So this is based on the observation that for the so-called super rigid rational curve, like the -1 curve, so this 1 over k cube is the same as the Gromov-Hitten invariant. And in this case, 1 over k squared is the same as the generalized dt invariant in that case. And in this case, the computation is the same as in the case of the first one. So anyway, in the second lecture, I will talk about cohomological dt theory. So yeah, I stop.